All right, let's get into it. Today, we're opening up the operations manual on a protocol that's really changing how AI remembers. It's called LLM Semantic Compression, or LSC for short. If you're an engineer building with large language models, well, this briefing is for you. We're going to show you how to solve that nagging memory bottleneck. Let's dive in.
So let me ask you something straight up. Is your retrieval augmented generation system, well, is it hitting a wall? Does it feel kind of bloated? Are you constantly fighting with context windows that fill up way too fast? Or maybe those token costs for inference are just getting out of hand. If any of that sounds familiar, you're not alone. It's a huge engineering problem, and it's exactly what we're going to tackle today.
We're going to walk through this just like a real ops manual. First up, we'll define what we mean by the AI memory wall. Then we'll introduce the LSC protocol as the fix. After that, we'll break down its core language, which is called HDLF, look at the just-in-time architecture that actually makes it all work, and finally, we'll get into its most exciting application, memory for autonomous agents.
Okay, Section 1, the AI memory wall. This really is the fundamental bottleneck in pretty much every modern RAG system out there. It's the core problem that a protocol like LSC was literally engineered to solve, so getting a grip on this is absolutely key. So here's the deal. When we store our information as just plain old natural language in our vector databases, we smash into three big problems. First, context window saturation. All those articles, pronouns, and filler words just eat up precious prompt space. Second, the inference cost gets crazy high. More words mean more tokens, and well, more tokens mean more money. And third, what we call cognitive noise. The LLM has to waste its cycles processing all that fluff instead of just focusing on the pure logic.
And this slide just lays it all out, doesn't it? On the left, you've got the traditional approach. It's noisy, it's inefficient, and it often leads to data drift from constantly summarizing things. But the LSC approach on the right, it's all about maximum density. We're talking about replacing that wordy text with pure logical nodes. This gives you 3 times the injection capacity and, this is the important part, it's a completely lossless conversion.
Which brings us right into Section 2, LSC, the compression protocol itself. Look, this isn't just about making things smaller. It's about making them more potent. It's about maximizing the actual, useful information that's packed into every single token.
Let's talk numbers, because this is where it gets really good. The first huge win for any engineering team is a 60 to 65% average reduction in token usage. And I want to be clear, this isn't some minor tweak. This is a fundamental shift in the cost and the efficiency of your entire AI system. And what does that saving get you? How about 3 times the context capacity? Yeah, that means for the exact same token cost, you can inject 3 times more meaningful, relevant knowledge into your prompt. And that dramatically improves the quality and the depth of your AI's responses.
Okay, but you know what's really fascinating about this slide? The number. It's 0, and that's probably the most critical feature of all. You see, unlike summarization, which always loses some detail, LSC is a structural transcoding process. It preserves 100% of the semantic meaning. Every single fact, every number, every relationship, it all stays perfectly intact.
So, let's jump into Section 3 and take a look under the hood to see how this actually works. The core tech here is the High-Density Logical Format, or HDLF. I want you to think of it as a language that's designed specifically for machines to read. It translates messy human prose into these clean, pure logical schematics.
HDLF is built on these really simple but powerful operators. The most important one is the arrow. It just means causes. It creates a clear, totally unambiguous causal link. So in the example, a server being offline directly causes a 404 error. Simple. There's just no room for misinterpretation.
The second key operator is this double colon, which simply means is defined as. You use this for creating logical equivalencies. So for example, LSC is defined as a type of semantic compression. Again, it's clean, it's precise, and it's perfectly machine-readable. Now this slide just puts it all together beautifully. On the left, you've got a typical sentence from a tech log. It's around 35 tokens. On the right, you have its HDLF equivalent. Just look at it. All the noise is just gone. What's left is pure logic. System causes error. Priority demands action. And the result? We go from 35 tokens down to just 14. That's a 60% saving with absolutely 0 loss of critical information. The deadline, the error code, the priority level, it's all perfectly preserved.
So how do we actually implement this in a real system? Well, that brings us to Section 4, the just-in-time architecture and semantic deduplication. This is really the operational backbone that makes LSC so incredibly powerful in a production environment.
The whole process has 4 clear phases. First, you ingest raw documents. Then you compress them into HDLF and you store them. Now, this compressed state is your database's default resting state. So when a query comes in, you retrieve only the relevant HDLF nodes. And only then, just in time, do you expand that tiny relevant fraction back into readable language. It is just incredibly efficient.
But this architecture also enables another just brilliant optimization, semantic deduplication. And the core idea is so simple but so powerful. You store a fact only one time, no matter how many thousands of documents it appears in. So here's how it works. A logical fact, let's say a token expiring in 3,600 seconds, gets encoded and stored exactly once. Every other document that mentions that exact same fact simply gets a pointer, a hash, back to that original entry. This completely eliminates massive data redundancy, and it means your system's efficiency actually gets better and better as your knowledge base grows. It scales exponentially.
Okay, let's move into our final section and see how all of this is building toward the future. We're talking about providing a truly effective, high-density memory for autonomous agents. And believe me, this is the next frontier in AI cognitive architecture.
So when an agent uses LSC for its long-term memory, 4 incredible things happen. 1, it can store vast amounts of information in a super compact way. 2, it can reason natively using those logical operators we talked about. 3, its cognitive focus is sharpened because it's only processing the signal, not the noise. And 4, maybe most importantly, because its memory is so structured and precise, its tendency to hallucinate, to just invent facts, is significantly reduced.
And honestly, this quote from the manual just says it all. When you free the LLM from processing syntactic filler, all the thes, ands, and buts, you allow it to dedicate its full attention to what really matters, the logical relationships between concepts. This is a direct upgrade to the machine's ability to think.
So we'll end with a question for you to think about. If an AI's memory is just a big pile of unstructured text, is it genuinely reasoning, or is it just performing some really advanced pattern matching? By shifting to a structured, logical format like HDLF, we're not just compressing data. We are fundamentally changing how an AI remembers, reasons, and ultimately, how it understands our world. That's it for this briefing.